Hello once again. The topic for this video is QR factorization. Now last time we showed how to take these three vectors, we actually used these three vectors and turn them into orthonormal vectors. Vectors that are orthogonal and with a norm of 1, with a length of 1. So we used the Gram-Schmidt orthogonalization process. We took these three vectors and turned them into these three vectors. Now notice so let's say this is the matrix A with the 3 column vectors. Let's call this matrix Q. If I take this matrix and multiply Q transpose times Q. So I write Q transpose, here's Q, multiply them. Well, remember Q transpose is each of the columns, each of the rows here is a column here. And when I multiply the rows times the columns here, I'm going to get 1 for the dot product of the vector with itself, because these columns are orthonormal. For everything else, I'm going to get zeros because they're orthogonal. This is nice. This is very nice structure for a matrix and is often something you want. But there's something else going on here. This is technical, but I've got to take this sheet up. Okay. So Q transpose Q equals I. This is true for any matrix with orthonormal columns. It could be they could be an R3, R4, or 5, it doesn't matter. Any matrix with orthonormal columns, when you take Q transpose Q, you're going to get I. Remember our original matrix, this was A. When we took these columns and did our Gram-Schmidt orthogonalization and then normalized each of the columns, we got this. Well, the question is, maybe there's a way to factor the original A into a matrix with orthonormal columns times another matrix. This could be useful. Just like, remember, we did a lot on factorization of a matrix in LU factorization or LDU factorization. Now, we've got another kind of factorization, QR, where Q would be a matrix with orthonormal columns. Well, if there is such an A equal to QR, multiply both sides by Q transpose. Well, Q transpose Q is just I, so R must have to be Q transpose A. So we can take Q transpose, apply it to A, multiply it by A, and we get this, which can be simplified to that. That's our R. R, that is our R. That's the R we wanted up here. In other words, we found a way that given a matrix like A, columns have to be independent. Not dependent, but independent. And we turn each of the columns into a set of orthonormal vectors. Then we can factor this A into a Q matrix and another matrix R. This is what's called the QR factorization. And this is also covered in chapter 4.4, and we'll see later how useful it can be. See you next time. Remember, you're going to have another set of videos on inner product spaces. There are, because we don't have a lecture on Monday, I won't be there on Monday, but I'm going to post some more videos in lieu of the lecture on Monday. And that is going to be on inner product spaces. There may be more than just 2 because there's not a good long Strang lecture or a good long lecture of any kind that I can find online on inner product spaces. So, and it's going to be based on Lay's chapter that I gave out in class last week. So I'll see you soon.